So the first questions here on the screen, asking us to consider a computer, and we're told that it has a 5 ohm resistance. It's connected to a 5-volt power supply. And what we need to find is the smallest capacitor needed to supply the current, or the computer with a current of at least 450 milliamps for 0.62 seconds in the event of a power failure. So what's really going on here is we have a 5-volt power supply. And the way we model a lot of electronic components that are a load or they draw current or something like that, we can model them as a resistance or a resistor. So there's a resistor that's our kind of simple model for this computer connected to a power supply. And we're told that there's a capacitor that in the event of a power failure can supply the current, or the required power or the current to keep the computer running for a little bit. So it's just like a flicker in the power or something like that. Sometimes it shuts off for just a second. You have this backup kind of capacitor. That can give you kind of some short-term backup power. So this has a resistance R, this has a resistance C, and that's the power supply voltage, which is 5 volts. So kind of, I guess if we're being really, really careful and detailed, what happens is if there's a power outage, we can get rid of the left branch of this circuit, which has the power supply, and what we just have is this capacitor here, and we could go back and label because this is obviously, recall when you have a battery or power supply, the big line of the symbol represents the positive terminal. This represents the negative terminal. So this will charge up the capacitor. So this is also positive and this is negative. So this is positive and this is negative. What we will get is some sort of current, which will vary as a function of time, but it's going to flow through this resistor. And the current and the amount of time it can flow for, kind of the decay envelope that we expect, is gonna depend on what the capacitance is and what the resistance is. So let's work through this. Maybe it's useful as well. What do we kind of expect? So if this power outage happens at t equals 0, that's when the capacitor starts discharging. When the capacitor is fully charged, the voltage is high. The voltage across, or the potential difference across the capacitor plates, and it can discharge at a high current. And that will decay with time. We should get some exponential decay that looks like that. So there'll be some sort of shape up here. This will be I max, or we could also call it I naught, whatever label we want to give it. And then what we're trying to figure out is we've been given a minimum time. I'll give that T subscript M for minimum. And we want to stay above 450 milliamps. I'm in. So perhaps somewhere along here. There's a minimum time for which we want to stay above a minimum current. And if the capacitance is too small, this curve would be down here. We wouldn't stay above this threshold. If the capacitance is really, really big, you can make it infinitely big, I guess. We would be above, but we're trying to find the exact perfect capacitance for when we can stay above 450 milliamps for 0.062 seconds, for whatever significance those quantities have. So the current is just going to be equal to some maximum initial value, which I'll call I naught, times the exponential minus t divided by RC. What we want to do is we want to solve this equation for the capacitance, but we want to solve this for the capacitance when we're kind of at the threshold of the min current and the minimum time. I've added subscript M on both the current and the time. And really all we need to do now is solve for C. So what I'll do first before taking a logarithm, I don't like the negative that's right here. So what I like to do is I like to flip this. And when we do that, we can flip the exponential as well, which just gets rid of that negative. We can take the natural log. Sometimes in physics, I like to write ln, which is the natural log or logarithm of base e. Sometimes you'll see people just simply write log, and if there's no base written here, it implies the same thing, but I'll try and use ln, the ln, or the natural log, just to be super clear about what we're doing. Okay, so we want to solve for c, so we just need to kind of cross multiply if that makes sense to you. So c is equal to the minimum time, that's 0.062 seconds, divided by the resistance times the natural log of I naught divided by Im. And it looks like we're done. The only real problem is we don't have this quantity I naught here, but we can figure it out super simple. So this is just an initial condition. It's how much current is flowing right away. So before the power was turned off, the computer and the backup power capacitor, if you want to think of it that way, was powered by this 5-volt power supply. Notice that everything is in parallel. This power supply, this capacitor, and this resistor, and they're all in parallel. And when certain branches of the circuit are in parallel, that means the same potential drop exists across all of them. So from here to here is a potential drop of 5 volts. Same from here to here, that kind of thing. So there's basically, if you imagine that the bottom is grounded, I don't know if you guys have learned what a ground is yet, but the potential difference across the capacitor and the resistor are both 5 volts because they're connected in parallel with this power supply. When the power supply is disconnected, initially we still have 5 volts on the capacitor. It maintains that voltage as long as it can while it starts to discharge. That also means there's 5 volts across the resistor. So we can just use Ohm's law to figure out what this current is. So what this really means is that I naught is equal to V naught divided by R. So that's just the initial voltage that the capacitor was charged up to, 5 volts, divided by the resistance which the current is passing through. So we can rewrite what we have here. V naught divided by the minimum current times the resistance. So this looks good to me. Let's square it off. And just to, one of the nice checks whenever you have an exponential or a logarithm or something like that, the units inside the logarithm should cancel out. So we have a voltage on top, and we know that IR is also equal to an voltage on the bottom of the fraction. So volts divided by volts, that'll cross off, and we're good. We are happy with the units in there. So that's a really simple, easy check to make sure that we know what we're doing. Okay, so that's problem 1. Problem 2, also on RC circuits. We're told to consider an RC circuit. We're given a capacitance and a resistance. We're also asked to suppose that this is initially charged to 4 volts by a power supply. There's a typo here. This is the capacitor, not the capacity. Hopefully you guys can follow along and that makes sense. So similar setup to what we have back here, where I said we had this getting charged to 5 volts. In this problem, we have a new capacitor, new resistor, and it's being charged to 4 volts, but conceptually the exact same. So this time we want to construct a plot of the potential difference across the resistor versus the time. as the capacitor discharges. And we want to also determine what the 1/2, quarter, and eighth, when those voltages occur at what times. So at what time do we reach half the original voltage? At what time do we reach a quarter of the original? That kind of thing. Okay, so we can actually proceed basically the same way. Like I said, the setup is the same. We have an RC circuit and it's charged up with a power supply. So we'll use the exact same equation that we had in the previous question. So this is the current flowing through the circuit. As a reminder, circuit will look something like this. And what we want to plot is, assuming that this is the positive and the negative plate, we have a capacitor and a resistor, so we're fully labeled now. Yeah, so the resistor is an ohmic material. If there's some current passing through it, then we can use that with Ohm's law to figure out what the potential drop is. So in other words, I is equal to V over R. This I here, I'm not writing it, but this one here is assumed to be a function of time. So you can imagine that I could write this as I of t, but I'm assuming it's easy to follow along and we don't necessarily need that. But either way, if we replace this with something from Ohm's law, then a quantity like the voltage will also be a function of time. So voltage is a function of time divided by R, replacing I is equal to V naught divided by R. So I'm just using Ohm's law twice here to replace either of the currents. And we have e to the minus t divided by RC. So these cross off, which is really handy. And notice that we want to construct our plot with kind of the ratio of the voltage at a particular time divided by whatever it initially was. So we can immediately kind of formulate our answer to comply with that. And we have e to the minus t RC. So to put this graph together, what I'm going to do is actually, I don't know what the specific time values are, but I know that we want to be figuring out what these half, quarter, and eighth points are. So I'm going to solve for time and plug in some points for V over V naught. So that might not sound super clear, so I'm just going to do it, and hopefully when you see it in front of you, it will make more sense. So if we solve this for time, maybe I will skip a few steps, but it equals RC logarithm of V naught over V. This has to be V naught over V. V naught is bigger because we know that the voltage is going to decay. This is the voltage at some times later, which has to be smaller, so a big number divided by a small number is a fraction greater than 1, which means if you have that in a logarithm, the logarithm will be positive, which means this whole term will come out positive, and we typically expect times to be positive. So this all makes sense. If you did your algebra wrong, you might end up with a logarithm of V over V naught, but that would give you negative times, which doesn't really typically make sense. Okay. So the time when V over V naught is a half, which is typically referred to as like a half-life, so I'll give it a t subscript to half. Is equal to 300 ohms times, what is the capacitance? 5.44. I'll convert this for you guys if you want to do it at home. So it's 10 to the minus 6 farads. Get rid of this for a second. Times the logarithm of 2. This is the logarithm of 2 because we're putting in V over V naught is equal to 2. Well, that gets flipped because of the orientation of this fraction right here. So it's ln 2. And we can figure out The other terms, I'm not going to write all this, but it would look like ln 4. Skip the writing again, and ln 8. And this bit here, this ln 4 can be written as 2 ln 2. Ln 8 can be 3 ln 2, that kind of thing. So what we get for answers is 1.3, if I remember correctly, 2.26, and 3.39. Okay. So from this, we kind of have, these are the x points, or sorry, our time, or the points along our horizontal axis. In case it's not clear what I've done here, this comes about from plugging in v over v naught, or sorry, yeah, v over v naught, sorry, equal to a half. V over v naught equal to a quarter, and v over v naught equal to an eighth. So these are the points along this vertical axis here. So now we can kind of just fill these in. I'll try and be as accurate as possible, but doing it by hand obviously is often a challenge. So there's the first point at 1.13. This ends up being milliseconds. 1.13 milliseconds. We're at a half of the original voltage at 2.26. Something like that. We're at a quarter of the original value, and then at 3.39, we are at an eighth of the original value. So it's somewhere maybe like right there. And now I will try my best to do a reasonable job of making a curve out of this. So we need to construct the graph. That was the original point of the question. So we essentially need to connect these. We want to connect them so the overall shape is that of some exponential decay. And of course, we need to end up at full value when time is equal to 0. So something like that. I think that was probably the best graph I've drawn all semester, so pretty proud of that. Okay. Yeah, so I think we found the times, we made the graphs. That's the end of the problem. I guess we could quickly box these off so no one gets lost when they watch later. Okay. So those two problems that we just did, RC circuits, now we're moving into the other half of what kind of comprises electromagnetism. We're going to do the magnetic part. You guys have already learned electrostatics, electrostatic forces, that kind of stuff. Now we're going to work with magnetism and magnetic forces. So the question on the screen now says a conducting bar of length L, which is 60 centimeters, suspended in a magnetic field. We're given a certain magnetic field value, 7.46 millitesla. That is a very typical value. One thing you guys have kind of learned is that when you're dealing with things, when you're dealing with electric charges, microcoulombs, nanocoulombs are perfectly acceptable, but like a single digit coulomb or 10 coulombs or something like that, very uncommon to encounter in the real world, and we try to usually write these problems as realistically as possible. So something like millitesla is very normal, and you can encounter things up to like half a Tesla or even like low single digit Teslas. There are bigger magnets that have many Tesla that exist in the world, but they're kind of found in research facilities and stuff like that with very specialized purposes. You won't really encounter that day to day. And things like the Earth's magnetic field, which are barely perceptible, that kind of thing, they're much, much smaller, obviously. But millitesla is a very, it's a reasonable unit is what I'm getting at. And hopefully you can gain familiarity with that as a reasonable size. The reason I'm going into this detail is if you ever have to calculate a magnetic field and it comes out to be 10 to the power of 8 Tesla, not to say it's a guarantee that something went wrong, but I would be surprised if everything was done right and you got an answer that large. Okay, so 7.46 millitesla. The bar is suspended in this region of magnetic field by some springs, and the springs also double as wires, which are carrying this current that's indicated here. So we're told that there are charge carrying electrons, which is not a surprise, move through the bar with a drift speed of 2.5 times 10 to the minus 5 meters per second when the current flows. We're told what the density of free charge carriers or electrons are per centimeter of bar, so we're given a linear density. And with all of this information, we're told that we need to figure out what the vertical distance the bar moves when the current is turned on. This is a lot to take in, but it's pretty simple if we break it down a little bit. So what's happening here is there's current passing through the bar, and this is a good reminder that when we describe currents, we conventionally, even though we know that there are electrons, which are the only current carrier in a solid, in a solution, things change a little bit, but in something like a metal conductor, it's the electrons that are moving. We know that those are negative, but we typically assign current to flow in the opposite direction, and we assume it has like a positive value. So when this arrow moves to the right, we assume there's some positive charge carrier that's moving this way. But as long as we all agree that current, as we denote it, is positive, then things like right-hand rules and all that kind of stuff that are required to figure out the direction of forces, they will all work. So let's really quickly just go over what's, we'll take a high-level view of what's going on here, and then maybe dive into the details. So we have current, which is moving through the bar. If we follow the arrows around, the current is moving to the right. And let's keep in our minds this current, let's pretend that it's a, for the time being, maybe we'll change this angle when we move through, we'll discuss it from a different perspective, but for right now, there's current that's flowing to the left. And there's a magnetic field that's in this kind of grayed area, and hopefully you guys will quickly become accustomed to the way that this is drawn usually. Magnetic field, as drawn here, is pointing out of the page. And the way that this is denoted is this circle with a dot in the middle. So I'm sure you guys saw all this in lecture, but it's great to go over it again. This is going out of the page, out of the blackboard if you're doing this in a lecture hall, out of kind of the surface, and this is into the page. And usually what is recommended to keep this straight in your head is imagine that you're looking at like an arrow from like a bow and arrow. And if an arrow was coming at you, it would look kind of like this. You would see something, there would be a point flying at you. That's the point right here. And you might see an X going at you if you're viewing from behind. So that would be kind of these feathers that traditionally are, I guess, are put on arrows or whatever. So that's kind of the mental model and how a good way to keep track of it. So yeah, so we have the current going to the right, or sorry, the left, excuse me, and this, I did a bad job there. Magnetic field out of the page. So let's figure out just kind of direction-wise, we don't need the magnitude yet, but we can write down the equation, but let's figure out kind of what's going to happen here and how things are going to move. So if you have a charged particle that's moving in a magnetic field, F equals the charge times the velocity. So this is where things get tricky. This is not the volume. This is not the voltage or potential difference. This is the speed, the velocity of the particle, and usually this is written with a lowercase v, which I tried to be consistent with, times the cross product with the magnetic field. Not sure what the expectation is for you guys with cross products, so what you can do is use scalars, and if you want to calculate the magnitude of the force, you can usually replace a cross product and vectors with scalars and sine theta, sine of the angle between the two. So in our case, we can easily just look at this right away. If I is pointing to the left in the plane of the page and B is pointing out of the page, then the angle between the two of those is 90. So we'll have, in our case, it will just be QVB. But the more important thing I want to focus on is this cross product. And what this tells us is that we can figure out this should be a vector, the direction of F, and this is what you get to do when there's a cross product. It comes about from the right-hand rule. So the way that I'm going to do this, and there are a couple different versions. You can do it with fingers. You can do it with your whole hand. I think I like the whole hand method, but it's up to you. I'll go through the method I use, and it's obviously hard when we're sitting in front of computer screens and not in front of each other, so you can't obviously see what I'm doing with my hand, but I'll try my best to explain it. So what I do, first of all, is I point my fingers, plural, so like all the fingers on my hand, I point them, and I guess it's important with a flat hand. In the direction of QV. And this is important. So I'm bringing the Q along with the velocity vector to account for the fact when you have positive charges or negative charges, right? So what's really happening, if we kind of break it down for a second, QV is always going to follow the direction of the current. As long as you've defined the current to be positive. So that's kind of a get out of jail free card, is just use that. But you could also think in your head, what directions are the electrons actually flowing? They're flowing to the right, but oh, they have a negative charge, so Q is negative, so we have to flip the direction of that vector. So it ends up pointing to the left. But QV will always point in the same direction as just the current. So if you're following along, you can imagine that your hand's probably in front of your palm is facing you, your hand is in front of your computer screen, and your fingers are pointing to the left, something like that. Bend or curl, kind of like closing your fist almost. And you keep your hand and your palm in the same position. You just move your fingers only. Fingers in the direction of B. So imagine that you, like I said, you have your fingers pointed to the left, your palm is kind of facing towards you, your palm is, if your wrist is flexible enough, your palm is kind of in the same, it's parallel to your screen, pointing in the direction of I. You bend and you curl your fingers, and they're kind of basically pointing away from the screen, kind of at yourself. So when you're in that position, look at the direction your thumb is pointing in. So the direction of your thumb is the same as the force. So if you do everything correctly and maybe go through the steps carefully and think about it and look at the orientation of your hand, the force will point up is what you should find. So something like this is the resultant force. So we're still just talking about what's going on conceptually here. So you have this bar, the force will point upwards, and you've got these springs here. So the springs will compress, and there will be a point as the springs compress where the force upwards from the current passing through the magnetic field will be equal to the compression, or equal and opposite to the compression in these two springs. So at some point we will reach equilibrium where the two forces sum together and they equal zero. So that's the idea of what's happening. But the key thing right now is that if I put a subscript B here, the force due to the magnetic field will point upwards. And then you'll have some sort of force due to the spring, give it a K for same letters as the spring constant, that will point downwards. And so at some point it will add up. Okay, so for lack of space, I'm going to erase this, and then we'll work actually solving the problem. And the other nice thing about this, I guess, and we've kind of talked about being active thinkers and that kind of stuff, as it goes for directions and when you can use scalars and when you can use vectors, and maybe there's times when you can use a scalar to do a calculation and you have to think about a direction at the end of the problem. The way we've done this, we've kind of already figured out what the directions are, so we can just move forward and work with scalars and take most of the numbers that need to go into these equations as absolute quantities, not worry if they're positive or negative or anything like that. Okay, so as I said, the bar is going to move until it reaches equilibrium. When we reach equilibrium, there are no net forces. One thing I'll say before I dive in, just to head off any questions, this is a bar that is hanging in a magnetic field. This bar is, there's two things you can either think about depending on how you want to accept the terms of the problem, I guess. We can pretend like these wires are very, very thin and don't have much mass, and therefore gravity doesn't count for much. Or you know that if this bar here has some mass, it will already have been pulling down on the springs. So the influence of gravity pulling down the springs, so I'm not about to, it's kind of already counterbalanced. So when we arrived at the problem and we're looking at it, kind of the amount that gravity will pull the springs downward has already been sorted out, and it's not within the scope of our problem. So I'm not intentionally ignoring it. Okay, so John had a question. Could you confirm if we're using QV cross B, or I assume, because I think positive or capital and lower cases are a little bit sketchy. I think what you're asking is, are we using QV cross B, or are we using lost my pen there for a second, like IL cross B or something like that. It doesn't really matter, but for in terms of solving the problem, the well, we're going to use the first one is the answer. And the reason we're going to use that is, if you notice, it actually doesn't really matter. We have the number of electrons, so that's going to give us, we can link that into a charge, and we can just say there's like n of them times the charge. We're given the velocity, so that would be v. What you come to realize is that nqv what would this be, I guess? This would be q divided by L is equal to I. They're basically the same thing. So they are very much equivalent equations. The only real difference is one of them makes more sense for the parameters that were given in the question. We could take the parameters we're given and we could use that to calculate what the current was, and it would get us to the exact same place. And we're kind of implicitly going to be doing that anyways. So I would just use, when it comes to solving questions on your own, I would just use whatever most conveniently lines up with what you're given and saves you the most trouble. But yeah, those are both kind of, usually adding the n, which we're going to do, like the number of electrons, is necessary here, but usually that equation comes about when you have like a single point charge or a point dipole or something like that moving. Yeah, when you have individual charges, it's weird to think about this in individual charges, but the fact that we have kind of a number that converts between kind of individual microscopic charges and this macroscopic current, let's do that. So yeah, we have, and maybe to make things really, really clear, what I can do is I'll write this as a capital Q, so that's the total charge. Velocity, actually we don't need the vectors anymore because I said that the angle between B and I, or B and QV, it's 90 degrees, so this sign here that's hanging out would become 1 anyways. So we have a velocity, we have a magnetic field. I'm writing this with a positive sign, and maybe I can make it explicit because I know this force points upwards. The force due to the springs points downwards. So we have 2 of them, so don't forget to count both of them. And they just follow Hooke's law. So spring constant times some sort of extension or compression in the spring. This is kind of our equation of motion, if you prefer. We're solving for delta y, but the real more challenging bit is what is kind of the total charge that's moving. So I don't really have a good variable to assign to this. I don't really know what I want to call it, so I just write it down. So Q is equal to 6.67 times 10 to the 22. And that's in units of per centimeter. We're just counting the number of things in a centimeter. So that's per unit length. We know that the bar has a length of 60 centimeters, and I'm converting to centimeters. So these both would cross off, this and this. So that is the total number of electrons in the bar that might be moving at one point, or at any given point. So I don't know if I'll actually write that again, but keep that in mind. What we want to solve for is delta y. So that's equal to capital Q VB divided by 2K. And I guess since we have the room, maybe I will write it out. But this would be kind of this question would be an exercise in keeping track of things that go into your calculator and managing kind of a big input. So that's the total charge. The velocity, or the speed, was 2.5 times 10 to the minus 5 meters. And the magnetic field was 7.46 times 10 to the minus 3 Tesla. This is already getting pretty huge. You can see what I mean. 4 numbers in the numerator. 3 of them have powers of 10 that you need to keep track of. And we had 2 springs, and the spring constant was 0.63 newtons per meter. So yeah, this would be fine if you guys put this in your calculator. You will get the answer. Normally, I would recommend on a test that you convert everything to SI units, and if you struggle keeping track of units, I would recommend you do that in this case. But I think if you can follow along and realize that these 2 centimeters are going to cross out, it is a lot more simple to keep this in centimeters than worrying about. I always struggle when there's something like 10 to the power of 22. If I convert that to meters, is it 10 to the power of 24 or is it 10 to the power of 20? I get lost a little bit with this per centimeters. So just that's another option in terms of your own problem solving skills and methods. Yeah, so I don't know what this is, but let's assume you guys did it. And really, this is the answer in terms of the physics before the calculator work. That's how much the bar moves. And I think the real crux of this is figuring out kind of what is the current, what is the direction, but also kind of the secret thing to get caught up on is there are 2 springs. Okay, so this is going to be our final problem. Pretty similar. We have charges moving in a magnetic field again. So what we're told is we have 2 identical point-like charges. They are initially traveling. There's another typo. Vertically with equal speed. So something like initial velocity for each of them looks something like this. But they're traveling in opposite directions and they enter this region of uniform magnetic field. That's right here again, it's this grayed area, and it's pointing out of the field, just like in the last problem. We're given kind of the dimensions, or at least part of the dimensions that are associated with either the region of magnetic field for this L, or just with the trajectory of motion for this L. Notice that they're both kind of confined within this box of L by L. Magnetic field points out of the page, as we said. It has a magnitude of 5 millitesla, another reasonable value. And we've got some pretty big charges here. We've got 0.3 millicoulombs. Each one's negative. And we've been given the masses, they're the same as well. So identical particles, negatively charged. We're told basically that there's kind of been an experimental consideration put into effect, a grounded shield that allows us to prevent, it prevents the Coulomb interaction between the two particles. So basically we can ignore the fact that these two charges would repel each other because of the electrostatic or the Coulomb interaction. And we want to calculate the speed of the particles so that when they kind of meet like they do here, they collide right in the center of this magnetic field. So this is pretty cool. This is a little bit different. This is the trajectory of kind of a free charge particle. So in the previous example, there was a force on the electrons or the current moving through that bar, but because the current was confined in two dimensions and really it could only move in one dimension, and the current was being driven through this bar, the charges simply moved in this direction maintained in the bar, and there was just a force that was felt, but they weren't free. The charges weren't really free to move independently in response to that force. But what you find here is they are. So you can imagine what would happen. You can come along. I'll probably end up erasing this too, but here's the initial velocity of charge Q2. So if we really quickly work through the cross products, remember the force is going to be equal to QV cross B. So we'll use the right-hand rule. If V is pointing up, but this is a negative charge, I'm actually going to be pointing, I'm not going to write it down, but I'll just walk through it verbally. I'm going to point my fingers downwards with my hand kind of in the plane of the page. So pointing towards the bottom of the screen, the magnetic field is out of the page. So now I've curled my fingers up out of the screen or out of the page, and my thumb is pointing to the left. What this actually means is at this point, the force, or as we know, Newton's second law, the force is equal to the acceleration. The acceleration points inwards. So I'll do acceleration in blue and velocity in red. You can imagine that if we pick out a new point in the trajectory, it's kind of dotted out here. Oh my gosh, that was really poor. The eraser, there we go. Something like that. The velocity is tangent to this trajectory. It points kind of at 45 degrees. You do the same method. QV, remember this is a negatively charged particle, so you have to start your fingers out pointing opposite the direction of this vector I just drew. You can curl your fingers out of the page and your thumb will point kind of down and to the left. And I think it'll be funny. It's really interesting. I mean, I'm not trying to laugh at the experience you guys have in exams, but it's funny when you go and you watch people writing physics exams and there's problems with magnetism or cross products on them, because you'll look around you and if you're in the Dalplex and there's 500 other people that are just kind of waving their wrists and their fingers around. It's pretty funny. So lastly, you can imagine that we look at what's going on, just looking at the direction at the very end before the collision. The velocity is off to the left. You go through the cross product again. Your fingers are pointing to the right initially. You curl them or bend them so they're pointing out of the page, and your thumb will point down. So I've done this to hopefully kind of drag up some memories. One what you're seeing here is a tangential velocity going through what looks to be sort of like a circle. You've got the acceleration pointing towards the center of that circle. So this is centripetal motion. And if we look at what's, we divide this in two, we can kind of define, this is a quarter circle. My drawing's not the greatest, but this is of radius L over 2. Notice here we divide this in half. Again, my drawing not the greatest, but we have L on one side, L over 2 on one side, L over 2 on the other. It's divided cleanly in half. So when we have centripetal motion, this problem gets really simple. We know if this charge Q2 goes on a circular trajectory with a radius L over 2, if this one goes on a circular trajectory, radius L over 2, the symmetry of the problem and the symmetry of this magnetic field, and the way it's laid out, basically tells us they will collide in the middle. So what are we going to do? We're going to leverage Newton's second law, which says that mass times acceleration is equal to whatever forces we've got. So if we have a centripetal acceleration, that's v squared over the radius of the circle. And in this case, our force is QBB. And just before I go on, I got to make sure. Yeah, so we're looking for the speed. Okay, I was looking for what is the initial speed? Have we been given the speed? We have not been given the speed because that's what we're solving for. So we have the mass of the particles. The radius we said we wanted to solve for was L over 2. So that becomes 2mv squared over L is equal to Q, and this is kind of like absolute value of Q at this point. This is just the magnitude of the charge. We've taken care of all the directionality with our drawing and the way we've set this up. So we can kind of ignore that. We can just type in 0.3 millicoulombs. It doesn't have to be minus 0.03 or 0.3. There's a V on both sides of this. So if we solve for the velocity, what we're left with is the magnitude of charge times B times L divided by 2m. I think in a lot of these problems, what you will find is you will find something like Q divided by M or M divided by Q. The mass charge ratio or the charge to mass ratio comes up in a lot. So the fact that we have Q over M here is to be expected. So I think we have everything. We have the magnetic field, that's 5 millitesla. We have the length, that's 1.5 meters. We have the charge, we have the mass. So this problem is done. So I think that's all I have for you guys tonight. We can go over anything that was confusing, or if there's any outstanding questions. But if not, that's it, and I'll take off shortly.